So, hi everyone. Today we have the pleasure to have Johannes from Equal Polytechnic, who will talk about recent advances in graph neural network robustness. So, Johannes is an assistant professor in the data science and mining group at the computer science department of Equal Polytechnic in France. Previously, he completed a postdoc under the supervision of Professor Michalis Johannes at École Polytechnique, and a PhD thesis on the spectral properties of the adjacency and Laplacian matrices under the supervision of Professor Andrew Walton in the mathematics department at Imperial College London. Johannes' current research is the area of graph representation learning with a focus on graph neural networks. So thank you, Johannes, for accepting our invitation. The floor is yours now for the presentation.
Thanks a lot, Mark. So yeah, thanks for the invitation. Today I would like to talk to you about recent advances in graph neural network robustness. And this is really the work of Sofiane and Yassine, two brilliant PhD students. They're also in the audience today. So I'm sure we'll hear from them sooner or later. And it was co-supervised by Henrik and Michalis, their professors at KTH and at École Polytechnique, respectively. So this is work done in a large team. And as promised, I want to start this presentation with what I called an accessible introduction. I hope it is an accessible introduction. Please stop me with questions if you have, if anything is unclear about these first few slides. I wanted to introduce the broad area in which I work, that is graph representation learning. So one way to frame this area of graph representation learning is to say anything we do, or almost anything we do in graph representation learning, is to attempt to learn informative representations of graph structured data. Whatever informative may mean, this definition varies in different contexts, obviously. And the reasonable question when presented with this goal, a reasonable question to ask would be, what is graph structured data? So when I talk about graph structured data, then I'm discussing this combination of two things. Firstly, we have an underlying graph. So a graph is a node set and an edge set. So we have a node set, these are entities, and an edge set, these are pairwise interactions of entities. They correspond to edges in this graph structure. And in graph structured data, we consider this graph structure and in addition assume that we have node features, so additional data, vectorial data on the nodes. This definition can be extended to also have vectorial data on the edges, the edge features, but in this talk that will not be the case. So graph structured data today will mean graph structure together with node features. The next one might ask, where does this kind of data arise? And I want to give some examples here to start things off. So graph structured data can be observed on the web, where we may, for example, choose to represent each node, each web blocks via node and connect them if they have hyperlinks to each other. There's many graphs in the application domain of molecules and proteins, and we are working on this. And Mohamed told me that some of you might also be interested in this. This is currently a hot topic in graph representation learning. Essentially, for example, in molecules, graphs naturally arise because we can represent atoms via nodes and then connect them if they have some chemical interaction or a chemical bond between each other, giving rise to a graph structure. Well, and we had a very good PhD student in our team a few years ago. He did a CFRIP PhD with Deezer. I think Mohamed, you met him as well. This is Guillaume Salah Galvan. And at Deezer, they have this big graph of users and songs. So both users and songs are represented via nodes, and edges are drawn if a user listens to a song. So in graph representation learning, we like to say that graph structured data is ubiquitous. It arises in many contexts. Well, and then a final question that's reasonable to ask at the beginning is, what can we learn from this kind of data? What's the interest of this kind of data? And here I want to give some examples of the typical learning tasks that we solve on this kind of data. Firstly, we can perform classification. This can be either at the node level or at the graph level. If performed at the node level, we may, for example, want to classify weblogs into Democratic supporting or Republican supporting if these are US political weblogs. And this was done famously by Lada Adamic when she collected this data set in 2005. Equally, we can classify at the graph level. So we can attach a single label to an entire graph. In addition to classification, we can obviously perform regression. And again, we can do so at the node or graph level. In this example with the molecule, we could, for example, regress the continuous antibiotic score. So we could regress to what degree could a certain molecule act as an antibiotic. This would be, for example, graph regression, where for an entire graph, for an entire molecule, we regress a continuous value, the propensity to act as a molecule. Well, and another commonly tackled task on graph structure data is link prediction. We may, for example, want to predict future links or edges between users and songs, and this is one approach to recommendation. We may want to predict what kind of songs a Deezer user is likely to listen to soon. Well, that's graph representation learning. This is a domain in which we have a rich data structure, interesting problems, and many models. And the dominating class of models at the moment are these graph neural networks that our work focuses on here in Paris. Graph neural networks, simply said, these are neural networks that take graph structured data as input. So these are neural networks defined on the graph structured data we have just considered. And most graph neural networks are part of this family of models called message passing neural networks. So almost all graph neural networks can be represented via this message passing formalism. And in message passing neural networks, the computational steps are split into two. The first of these steps is the message passing step. In the message passing step, we aggregate information over neighborhoods in the graph. Aggregate can mean many things. The canonical example of a graph neural network, one of the first graph neural networks is this graph convolutional network. And in the graph convolutional network, we take weighted sums over neighborhoods in the graph, as illustrated here. So the messages received by node 2, or the message received by node 2 is computed by summing the node features of all its neighbors. These are node 1, 4, and 7, and then weighting them by the square root of their degrees, and then weighting the whole sum by the square root of the degree of node 2. So in the graph convolutional network, we take weighted sums over neighborhoods, and the weights in these sums are defined in terms of the node degrees. And in this way, each node receives a message in the message passing step. So node 2 will receive a message that is calculated as a function of the representations of 1, 4, and 7. And equally, node 3 will receive a message that is calculated as a function of the representations of nodes 1 and 5. So in the message passing step, we use the graph structure. The second step in message passing neural networks is this update step. The update step is performed node-wise, and therefore is independent of the graph structure. The update step typically doesn't receive so much attention in our literature because in the update step we commonly apply a multi-layer perceptron, or in this example here, a single linear layer to the combination of the previous representation of a node and the message received. So in the graph convolutional network, we sum the two. Then we apply a trainable weight matrix W to this vector and a nonlinear activation function. These are the computations performed in the update step, and hence we are able to look at the graph convolutional network or a layer of the graph convolutional network where this message passing step can be encoded by a multiplication of some left and right normalized adjacency matrix onto the node features X. And the update step is encoded by some trainable weight matrix and nonlinear activation function as discussed. And then, as we do in deep learning, right, we compose these functions. We have a function here corresponding to a single layer of this model, and we compose these functions to form deeper models. This is a three-layer graph convolutional network. We have three trainable weight matrices. We have three message passing steps as encoded by these normalized adjacency matrices, and we feed in our initial node features X. This will allow us to perform some node level or graph level task. Right, so this is my general introduction to graph representation learning and graph neural networks. Maybe it could be productive to take questions already now, because if this is unclear, the rest might not be that enjoyable. So are there any questions in the audience at this stage already? Or has this been somewhat clear so far?
It seems to be clear. So for the audience, if you have any questions, please use the Q&A to ask questions. So there is one question so far. Can you explain on how you use the MLP?
Nice, great. Thanks for the question. That was indeed somewhat unclear. So here in this graph convolutional network, in my illustration of it, we only use a single linear layer. So here we use, it's almost, it would be unfair to call it a multi-layer perceptron, right? But essentially to the representation of every node, we apply a single linear layer to transform the representation of that node. So we apply the MLP node-wise. And here in this graph convolutional network, we have a single weight matrix. And we could easily choose to apply a second weight matrix outside of it here, and then apply another activation function outside. So we could make this update step arbitrarily deep. But you're right, in this illustration here, I only work with a single linear layer, and this is not necessarily a multi-layer perceptron. And the next question is extremely nice. Also recently, the CAN network, CANs seem interesting. To be honest, I first heard about these CANs on Monday, and so I'm no expert in them at all. But to me, it seems that if they really work as well as people say, then yes, we can expect a flood of papers where all of deep learning gets redone, where MLPs are replaced by CANs. This thing can happen in graph neural networks. If CANs indeed work better and are more efficient, then indeed the update step should be replaced by CANs. And yeah, we'll see, I guess. Maybe NeurIPS is too soon, but probably at the next big conference. Let's see. Yeah, I guess ICLR next year, we might have a lot of CAN GNNs. Good question. Great, so please. I recently ported the Python implementation for us. I would love to work on experimenting this in GNN. Yeah, I think this is a very promising direction. All results point towards this being a good implementation, right? A good model for learning general transformations of vectors. I have to say that there is some work from 2019 called Simplified Graph Neural Networks, and also work by Guillaume in our group. I think this is the Ask GAE one. Essentially, there is some work which shows that on many benchmarks in graphs, the heavy lifting is done by the message passing step, and the update step is often insignificant to the performance. So when trying to extend GNNs to CANs, it might be that one observes a little performance difference, and this is not because CANs are better, insignificantly better than MLPs. This might just be because MLPs don't make a big difference on some data sets. So possibly you have to choose your tasks carefully there. I would evaluate the CAN GNNs on graph regression, because graph regression is a task where the updates that matters more, and at scale ideally, because at scale also the updates that matters more. Possibly it's also good to work with graph level, because at the graph level we have an MLP readout which makes a difference. So that is to say that that's a nice direction, a good idea, and you have to choose carefully in which context you test this, because in some contexts the update step doesn't matter too much. We found this in an ICLR workshop paper where we specified the update step that we published 3 years ago. So we have all the experiments there which show where and when the update step matters. I don't remember how we called it, specifying the weights of the graph neural network or something like this.
By the way, on a related question, what are the typical dimensions in GCNs, like in practice? Because like this CAN seems to work well in, let's say, in low dimension with fewer parameters, but scales poorly with high dimension. With like you have some accuracy, but you pay the cost of longer training at high dimension. So is there some problem you have small dimension of the features?
I mean, the typical GNNs don't tend to involve that many parameters, right? The dimensions tend to be rather low, but I guess the CANs would reduce it even further. Yeah, good point. But yeah, like I said initially, I started looking at these on Monday, so 2 days ago, so I really can't talk much. Well, good point. Good point.
Okay, I guess we can move forward.
Great, and please keep asking questions. I think this is what will make the talk interesting if we manage to discuss the work instead of just presenting it. So graph neural networks have already had some impact. There's been quite a lot of empirical and theoretical research, and here I want to highlight different streams of theoretical research. A lot of theoretical work has been on the sorry, let me quickly. The chat messages disappear. Amazing. Sorry. A lot of theoretical work has been on the expressivity analysis of graph neural networks. And in this stream of work, we analyze to what the differences in graphs our graph neural networks are sensitive, and what differences in graphs our graph neural networks are blind to by design. So there's some famous examples of relatively small graphs, but obviously we scale to larger graphs where standard graph convolutional network, for example, cannot distinguish two different graphs because by design it is blind to these differences. And so there's been a lot of theoretical work classifying what differences we are able to observe in the representations of GNNs, what differences in input graphs, and what differences in input graphs we are blind to by design, and then how can we build graph neural networks that are able to distinguish a greater class of graphs. So really a lot of work has been done on that. There's been quite a lot of theoretical work as well on the topic of oversmoothing and oversquashing. These are bottlenecks or theoretical problems that arise in graph neural networks. So maybe let me summarize these in 1 or 2 sentences. The problem of oversmoothing in graph neural networks refers to the fact that as we for deep graph neural networks, we can observe that all node representations converge to the same vector. To me, that's an intuitive phenomenon because we discussed how in the message passing step we average over neighborhoods. And if we keep averaging, then we are likely to converge to a grand mean at some point. And some people say this is a problem because when we do deep learning, we want to use deep models. And for graph neural networks, if we use as many message passing steps as we have layers in our model, then we tend to smooth the representations too much to an extent where we may over-smooth, and there's some work that aims to reduce the smoothing done or control the smoothing done. So as to give us the ability to fit deep graph neural networks still with many message passing steps while maintaining the ability to distinguish nodes. And over-squashing is a different phenomenon that's also a bottleneck in graph neural networks that is present by design. Over-squashing has different definitions, but I'm just going to give one maybe. So, in graphs, we can look at the one-hop neighbors of nodes, and then we can also look at the two-hop neighbors of nodes. And by two-hop neighbors, we refer to neighbors of neighbors. And typically, real-world graphs at least expand exponentially at a local scale. So the two-hop may be exponentially bigger than the one-hop, and the three-hop will be exponentially bigger than the two-hop. If every node has 3 or 4 neighbors, we initially have 4 neighbors, and then each of those 4 neighbors may have 3 or 4 different neighbors, and these neighbors may again have 3 or 4 different neighbors. And in that sense, these hops increase in size exponentially, and over-squashing refers to the problem that as we fit deeper models, we are essentially attempting to fit an exponentially growing amount of information into a fixed size vector. And if we want to fit all this information in our fixed size vector, then we're doomed. So this is one way to pose the over-squashing problem. And there's also some really good work on this by Francesco Giovanni. A first stream of theoretical research, and this will be our focus today, is the robustness to adversarial robustness and noise of these graph neural networks. Since they're used more and more in industry, and I'll show examples of this later on, the robustness of these models becomes more and more important. I think it would be remiss to not mention the name Stefan Günnemann when talking about robustness of graph neural networks. The group of Stefan Günnemann does a lot of excellent work on this topic. And we've also worked on this, notably Mohammed, when he was in our group, he published a paper at AIDRC where he did some very nice random matrix theory analysis, and we discussed these models in the context of robustness. So we've also begun working on this topic a few years ago. Today we expand on that. And in industry, they are much used. So in Google Maps, they are deployed to estimate the time of arrival in large cities. And Sofiane found this nice example of someone disturbing the routing in large cities by what can be understood as an adversarial attack on the Google Maps routing system. Twitter has done much work in the past on the use of graph neural networks. They had this very strong team around Michael Bronstein. Graph neural networks are extensively used for recommendation at Amazon, Alibaba, Pinterest, and Uber Eats. All of these companies have published in one shape or form on the use of graph neural networks. And then what might be interesting to the computational biologists among you is that in recent years, 2 new antibiotics were discovered with pipelines that involve graph neural networks. So this is a relatively good success. And just a few months ago, LinkedIn also released a paper where they discuss how graph neural networks are used for all kinds of tasks on LinkedIn. And with this, I think we're ready to discuss the 2 papers that I came here to present today. Note that the first authors are Yasin and Sofiane in the audience. They contributed equally to this work. Last week, we discussed this work at ICLR and met Mohammed as well. What is the actual, so there's an audience question, thanks a lot for that. What is the actual relation between GNNs and knowledge graphs? That's a nice question. So graph neural networks are defined on graph structured data, and knowledge graphs, in my understanding, they are graphs where we have edge types and sometimes node types. So here in knowledge graphs, we extend this definition that I gave of graph structured data slightly, because now we have typed nodes and typed edges. But equally, we can relatively easily extend graph neural networks to operate on these kind of typed structures, so to operate on knowledge graphs. And this is being done. So there's much work on knowledge graph completion, on the embedding of nodes and knowledge graphs using graph neural networks. Notably, last week at ICLR, I met Michael Galkin and his team. They presented a new paper at ICLR where they show how well they generalize. So they train a graph neural network on 3 knowledge graphs, and then they generalize to knowledge graphs from all kinds of different domains using this trained model. So from what I've seen, graph neural networks do relatively well on knowledge graphs and are already much used on these. Nice question. So we call this bounding the expected robustness of graph neural networks subject to node feature attacks. And so we're talking about adversarial robustness. I thought I'd give a small insight into my understanding of this domain. My understanding is that in adversarial attacks on models, the goal is typically to apply a small change to the input with the goal of achieving a large change in the output of the model. So this famous example, this famous visualization of Goodfellow et al. Is one where we have this CNN applied to an image of a panda, and with some confidence it makes the correct classification. This image contains a panda. And then they add a small amount of noise, so they sample some noise, multiplied by a small factor, added to the panda image, and with high confidence, the CNN predicts that the image contains a given. So here, this is an example of a successful adversarial attack where we have some input, we apply a small amount of noise, and we drastically change the output, in this case, to a wrong prediction with high confidence. And now we're discussing graphs here, so we need to see what do graph adversarial attacks look like. So to make this a bit more precise, here we're discussing small input changes, large input changes. Let's quantify this. To quantify this, we need a distance in the input space. And here, Sofiane and Yassine have this rather nice general definition. We're looking at the distance on the graph structure space. So graphs are represented or can be represented by the adjacency matrix. And so we can measure the distance of two adjacency matrices as here in the 2 norm. And note that since we're operating on node sets, the sets have no order, hence we need to account for permutations of these node sets in order to get a sensible distance measure. So these permutation matrices P, they allow us to align these 2 graphs as closely as possible. So this is a measure on the graph space, and we're working with graph structure data. So in addition to the graph structure, we have some node features. And again, this is a measure of distance in the structure, in the feature space. And we account for permutations of nodes once more. So this is a rather general definition of distance in the input space, where the input space is the combination of a graph structure and the node features. Here I've chosen to present this for the 2 norm, but we can apply any norm we like to these 2 separate input spaces, and we have general weights alpha and beta on these 2 spaces. If we want to simply look at the feature space, we can set beta to 1 and alpha to 0 and ignore differences in graph structure. So this will allow us to quantify what a small change in the input space is. So we want to generate a second graph, G tilde, X tilde, that is close in the distance that we give here to our original input graph G and X. And then with such small there's another question, awesome. GNNs look an interesting alternative to FFN blocks in transformers model language with nodes as function of the attention scores. Are there, at the best of your knowledge, applications to language? Yes, there's applications to language. So there's much to say, and thanks, that's a nice question. So Yassine, first project with me, we published this at NeurIPS workshop earlier this year or late last year. This was GNNs for text classification. So we've tried this, but this is challenging. I mean, it's difficult to beat a transformer with a GNN alone. Transformers are very general, very large models. As everyone knows, they are state of the art on text data. but there's interesting combinations of transformers and GNN, and there's a lot of people discussing how we might be able to infuse some understanding of the world into large language models via knowledge graphs. And I think if we do so, then a combination of a large language model and the GNN is an obvious choice. So yes, there's some work on this. And since you say that GNNs provide an interesting perspective of transformers, this I also agree with. There was a blog post maybe 3 years ago where I forgot who this was, but someone noticed that the transformer architecture can be seen as a graph neural network on a complete graph, because in the transformer architecture we obtain these, or we calculate this cross attention between any two input tokens, and this could correspond to learning edge weights on a complete graph, and then the multiplication of this attention matrix that we obtain with the it's very key value. So the attention matrix with the value representation of the input tokens could message passing on this complete graph of the value representation. So if one wants, one can think of transformers as GNNs on complete graphs. The two are intricately linked, and I think in future we'll see multimodal models on these. In fact, our group, Michalis Vasilianis, they published proto-text last year. I think this was at AAAI, where they indeed already combine GNN with an LLM, and they're able to describe proteins in that way. Okay, so sorry, I probably said too much, but an interesting question. There's much to say about this. This distance function here allows us to quantify differences in the input. Recall that we want this to be small, and we want the change in the output to be large. So we need, sorry?
About this distance here, do you assume some normalization on the node features? Because if you just apply the permutation, you may have the distance large, like the distance can be large if they are not normalized like in a certain manner, no?
Yeah, this is a good question. Well, I think here we don't absolutely need to assume a normalization. Like if we consider the data set of graphs and we picked graphs from this data set, then indeed we'd need to normalize them all to be on the same scale. But here we take a different approach where we take graphs in the data set and we want to explore graphs that are in a small neighborhood of these. And okay. So in our considerations, we upper bound this distance and therefore don't need to normalize these features. Instead, we by definition sample features that are nearby. So different ways to think about this. Here we don't discuss normalization, but if we post it in this first way, we'd have to. Good question.
Thanks.
And we have some distance in the output space to allow us to quantify what a large change in the output may be. Here we have the one norm, for example. So if we have some graph structured, if we have a function processing graph structured data, we call this function f, then we want a large distance in this output space. In other words, we may want the one norm of the difference of outputs of f to be large. So here we have a nice visualization of what I just said. We have some input graph x. We explore a relatively small neighborhood of this input graph and then observe 4 graphs in this small neighborhood. How big is the difference in the output? So we want a successful adversarial attack makes a small perturbation in the input space and achieves a large perturbation in the output space. And from this point of view, and equipped with these two distances, in our ICLR paper, we define what we called expected adversarial robustness. And then, sorry, this is where we have a lot of equations, but given what we've just discussed, this is relatively simple. So here we consider balls around our input graph. So we consider the set of graphs for which our input distance is less than epsilon. So that's this circle that we have here. The this set of graphs around our input graph, we denote by B alpha beta. So that's a ball around our input graph, and we define the expected vulnerability. This is not yet robustness, the expected vulnerability to be the probability of finding a graph in this ball around our input graph for which the output distance is at least sigma. So this may look complex, but it's actually not so hard. It is built on what we've just said. We look at graphs in the input space that are nearby, and we look at what is the probability that for such graphs, our output deviates from the target output by at least sigma. This expected vulnerability is different to what is typically considered in adversarial robustness, at least for graphs. For graphs, previously, we always looked at worst case adversarial robustness. So we still considered graphs in this ball around the input, but it would be sufficient for us if any one such graph produced a different classification. So in that sense, previous quantifications of vulnerability were worst case, because the existence of a single graph for which we make a wrong prediction is sufficient to say we are not robust. And then here we extend this slightly. We look at this set of graphs around the neighborhood, and we look at the probability of any one of these allowing us to achieve a wrong prediction. So in that sense, ours is more probabilistic and gives a sense of the average robustness, the expected robustness of a graph-based function. And so hence we say that a graph-based function f is robust with respect to the distances we define on the input and output space if we can upper bound this expected vulnerability by some function gamma. Do you have questions about this? This might be the most technical part of the talk. So recall that graph neural networks take both a graph and node features as input. One weakness in the literature, or one feature of the literature, was that many works in this domain of adversarial attacks on GNNs, they focus on structural attacks, and very little work was done on attacks on the node features. And hence we focus on node features to cover this gap. And we proved a rather nice bound, a theoretical bound on this expected adversarial robustness that we defined. This is in terms of normalized walks, so the graph structure matters, but it's also in terms of this product of weight matrices that arise in graph neural networks. Maybe only one thing to notice that's of importance here. This upper bound depends on the product of weight matrices, as one would expect, right? If we upper bound the output of some function, this bound almost always will be a function of its parameters, these weight matrices. And so we notice that if we control this product of weight matrices, if we reduce this product of weight matrices, our upper bound is smaller, and therefore our graph convolutional network will be more robust. So we looked for ways of reducing this norm of weight matrices. And well, Sofiane and Yasin thought that orthonormal matrices have norm 1. Could we use this? According to our bound, graph neural networks that have orthonormal weight matrices should be more robust. And then they found this a relatively old algorithm. It's called the Bjerg orthonormalization algorithm, where given some matrix, we can iteratively approach its nearest orthonormal matrix. So it's an iterative scheme where we expand, we have some tail expansion, and we approach the nearest orthonormal matrix. And we simply include such steps. We simply include this orthonormalization algorithm in the forward path of the GCN. And we call this model GCORN, graph convolutional orthonormal robust neural network, maybe a long name, but essentially we wanted to get this orthonormal in there. So we include this orthonormalization a step in several of these open normalization steps in the forward path of the model. And in this way, we encourage orthonormality of the weight. That's rather nice because this orthonormalization algorithm is differentiable. So we can take this into account during model training and can differentiate through it. So we have the theoretical result presented earlier. We have a methodological change. Let's observe how this works in practice. This actually tends to work relatively well. So we wanted to focus on feature-based attacks. There we outperform some existing methods in several cases, as shown here. So we have different, we have the graph convolutional network here. We have some defense approaches on graph neural networks. We have a range of different data sets, so 5 different node classification data sets, and 4 different attack scenarios where 2 are just random perturbations of our input. And we're displaying accuracy, so higher is better. And then often we are doing relatively well with our approach. And we even observed that this also works for structure-based attacks as displayed here, and then also the combination of structure and feature attacks. That's somewhat unsurprising because Sufyan and Yassine were able to prove similar bounds. We showed the bound here for feature-based attacks, but similar bounds for structure-based attacks. And this approach of controlling the norm of the weight matrices is relatively general, so it works in different attack scenarios. Right, and one thing to say maybe is that this approach incurs some computational costs, and so do many other defenses on graph neural networks. So in our second project, we proposed something far simpler, much faster. And we published this at AAAI earlier this year. The problem that we tackle here is, as I teased already, most defense approaches have a relatively high computational complexity and training time, and often this scales with the input size. So as the graph grows, these models become more expensive. And the simple solution approach that Sufyan and Yassine thought of was to add random noise to the hidden states of our graph neural network. So this is something that I hadn't seen before, at least. We've seen models that perturb the output. We've seen models that perturb the input. They thought, what happens if we perturb the hidden states of our graph neural network? This is the solution approach. Obviously, we didn't pull this out of thin air. So we first proved some theorem. We have some theory to motivate this model. And then we also have some empirical analysis. But I simply wanted to present our model first. Our model is a standard graph neural network. And after some message passing rounds, we add random noise to the hidden states. These are the theoretical results that motivate this. So here in this project, we don't work with expected robustness. We work with a rather similar definition of robustness, the adversarial risk. So I didn't include this in the slides, but we have it in the paper. And we're able to upper bound the vulnerability in the context of this risk with these 2 bounds here, one for the GCN and another for the GIN. The graph isomorphism network is another popular graph neural network. And we're considering models here where noise has been added to the hidden states, and you can see that we find this parameter beta that controls the standard deviation of our noise in the denominator. So the larger this beta, the less vulnerable our model becomes. To some degree, that's intuitive. If we have a very large beta, if we add noise with a very high standard deviation to our hidden states, then the model becomes unpredictable. And in that sense, it's very robust to different inputs.
But how does affect the performance? Because if you add noise, maybe you get...
Exactly right, yeah. The more noise we add, the lower the accuracy, but the higher the robustness. So by adding noise, we start to introduce this controllable trade-off between robustness and accuracy. you spotted it right away. This is a rather cheap thing to do, right? We simply need to sample random Gaussian noise. We add it to our hidden states. This doesn't come at a large cost. And in practice, it works relatively well. Like we even sometimes outperform existing defenses. So again, this is node classification subject to a specific kind of attack, 4 different data sets, different attack budgets. And we see in some cases, we outperform a range of benchmarks. Keep in mind that our model is very fast to train. All we do is perturb the hidden states. And actually, it's also rather simple to combine with other defense methods. If we simply perturb the hidden states of other GNN defense methods, from what we've observed, we always improve the performance. So in this sense, this is kind of a nice and simple trick. If you want to increase the robustness of your model, you might want to perturb the hidden states, is what we're saying here. Good, these are the 2 works I wanted to present. I briefly included this slide because Mohammed told me some of you might care about biological applications. So here we have kind of a lot of our past work on GNNs in one slide. We've worked a lot on GNNs in the past years, and we're working on biological applications. We already have 1 workshop paper from 2 years ago that was accepted, and some other ones that we'll start submitting soon. All right, to conclude, graph representation learning is very active, both in academia and industry. Graph neural networks are versatile, powerful, and you might want to consider using them. They're fun to work on, and it's a nice research community. And specifically with regards to do 2 projects I presented today, we've observed that the introduction of noise to the hidden states and the orthonormalization of weights, these are viable avenues towards more robust graph neural networks. And these are inserted into a rich literature of robust graph neural networks. There's other viable avenues to produce more robust graph neural networks. So thanks again for the invitation. Thanks for listening, and especially thanks for your questions. I think I went fast enough to leave enough time for a few more questions if you'd like to ask. Thank you.
Yes, thank you, Johannes. Indeed, we have like 10 minutes left if the audience has any question.
Great, there is one. A couple of questions. On the first paper, how can you keep the lower bound gamma low for a large network high L? This is a good question. It's not that easy for Sofiane and Yatin to talk because of the setup of the Zoom room, isn't it, Mohammed? They need to post replies in text form.
I think it's better like that you read the questions out loud, and maybe they can comment on the chat as well.
Okay.
The audience maybe don't see all the questions.
Yeah, maybe I'll reply to this one. Indeed, this is well observed. The larger L, can we get I'll definitely, can we get a copy of the slides? Mohammed, I can just send them to you and you can send them to people, or I can put them on my website, but I've not updated it in more than a year. Maybe it's easier if I send. Could we do this, Mohammed, that I send you the slides and you send it to attendees, or
yeah,
is it easier?
If you can send me just a link to your website, to the slides on your website, and then I can share it on LinkedIn. So we have a post that is related to this talk. And other than that, please feel free to reach out to me via email or LinkedIn to ask for them.
Great, let's do that. So after I think next week is the NERV's paper submission deadline. After this, I'll finally update my website and then put them on there. But sorry, so back to the first question you asked. For large networks, how can we keep a lower bound? This is a good question. So the deeper the network, the larger this capital L, the less control we have on the output, right? And this is simply a feature of our theoretical bound. I mean, the deeper the network, the easier or the bigger could be the impact of a perturbation. I expect that our defense method, the G-corn method, will actually show greater improvements in large depths, because since we try to control the norm of these weight matrices to be approximately 1, we are working with transformations that are approximately isometry, so they roughly preserve the length of these hidden states. And so I would expect that, especially at depth, a standard graph neural network has a very large term here. The more layers we have, the potentially larger this term gets. Whereas for us, this term will grow slower because we continuously decrease it iteratively throughout training. So, right, the deeper the network, the potentially bigger the impact of attacks, at least in theory here. And I think also the greater the benefits of our defense method. But I'm not sure whether we ran experiments on this. So this is my understanding based on the theory. And the second question, and yeah, Sofiane and Yassine, if you did run experiments on this, then feel free to comment in the chat, I suppose. The second question is, if I got it right, you're adding the Gaussian noise only in the last softmax layer. How much increased robustness or lower accuracy do you get by inserting it in each layer? Yes, this is also a good question. I didn't run these experiments. I think it's Sofiane and or Yassine who know. So you should contact them in some form. They're also in the chat here. I remember Sofiane saying that if he adds the noise to all hidden states, to all layers, the robustness and performance is decreased quite a lot, to the degree where this is not a viable method. So I think it is crucial to our approach that we only add noise to one layer, and we observed it to be better to the last one. Yassine replies, we set the number of layers equal to 2, which is the standard choice in GNNs because of the over-smoothing problem. I think this may have been in the context of the first project.
By the way,
maybe
when you add this, is it added like before training or after training? Like
I think during training we add it, and then I think during inference at test time we actually don't add it anymore.
Okay, so it's a kind of a regularization setup, I see. And do you like? So you just remove you take like you take n equal to 0 during inference, or you do some rescaling because you.
No, I think we take n equal to 0 during inference, but I'm not 100% sure on this. It might be best to check this on the paper or with Sofiane and Yassine. But from what I remember, we said we only have n during training and then set it to 0 during inference, correct? And don't rescale.
Somehow close to dropout in like organization, but dropout is like you multiply the features by some mask, but at inference, when you remove the dropout, you should rescale the matrices somehow to like to make sure that like there is no bias added by this dropout. So I'm wondering if the same thing happens here.
I doubt it, because in dropout, in expectation, you reduce the size of the hidden states, right? Or the length of these hidden state vectors. Whereas for us, in expectation, we maintain the length of the hidden states. So I would guess that somehow normalization doesn't give us a big advantage. But this is a really nice way to think about the method. I never made this connection to dropout. So yeah, that's cool. Yeah, nice. Are there any other questions? Sofiane replies, the noise is only added during training. Basically, it's a sampling and a sum operation. It is actually a kind of dropout. We have also seen that adding noise between the first and the second layer is the best, is better. The intuition is that in that phase, it's rather similar to adversarial training, while if you only add it at the end, it rather perturbs a lot the classification of clean accuracy. Oh, and then what I previously said was wrong. Sorry, we only added in one layer, as I correctly stated, but we added in the first layers rather than the last one. My mistake. Thanks, Sofian.
Thanks. I think we are right on time. So if there are not any further questions, and if there are any, feel free to reach out to us, to Johannes or myself. We'll be happy to answer. Thank you very much, Johannes, for accepting the invitation. And yeah,
thanks. It's been a pleasure talking to you, and thanks for all the questions. Sofian and Yasin are graduating next year. They did this work. They will be looking for jobs soon. Thank you.
Thanks. Have a nice day.
You too. Bye.
Bye.